Thank you so much. Thank you, Sherry. It's been great to be here, and I'm very inspired by this day of talks, meeting with you all. And thank you to Sarah as well. Thank you to the LIDS organizers. Thanks to everyone for making this so smooth. So yeah, this is called OlmoEarth now. We just rebranded a couple months ago, and so OlmoEarth is the name of this new foundation model and platform that I'll be telling you guys about. We launched this, as Sherry said, just last week, actually. So I said in the abstract, Earth AI is surging in popularity, and I got feedback on this abstract from my wife, which I always do, and she said, hey, really love what you're doing, but also it might be a bit of a stretch to say this is surging. And so I looked it up to prove to her that this was in fact the case, and here's the interest over time, and I think it's rightfully that inflection point is somewhere around mid this year, and so she believed me, but then to put it in context, of course, the LLM space has been rather dominant in the AI world of late. So in the end, we're both right, and our marriage is still strong. But in more serious terms, like I think in general, AGI is receiving a ton of press, right? It's like basically constant, and I think it's maybe not the thing we need to be talking about. We may or may not build AGI, and different people will give you a different timeline for when that's going to occur. I don't think necessarily that just because we build AGI, if we do in fact build it, and we can talk about what the real definition is if we want, but even if we get there, it's not going to magically solve all of our problems. And here are two papers, one from Microsoft and one from Anthropic about, or maybe it's OpenAI, about kind of what it would mean and what would happen once we have AGI, and perhaps we have sparks of AGI at this point. I think these are basically not the thing we should be focused on. I think we should be focusing on steering artificial intelligence towards our highest ideals, towards what we think really matters from the outset. So I'm from AI2, as Sherry mentioned, the Allen Institute for Artificial Intelligence. This is a nonprofit AI research institute that was founded about 10 years ago by the late Paul Allen, Microsoft co-founder Paul Allen, and our mission is to build AI for some of the world's big challenges. And we build AI, I would say, a little bit differently from perhaps from the norm. So we first of all center the user from the outset of R&D, and in our case that means literally speaking to users from the very beginning of the project, from before we even start the model research and development project. We're talking with the users who are going to be the recipients of that technology, so we can ensure that whatever we're building is closely aligned with their interests, and that might be in agriculture and food security, or wildfire resilience, or deforestation cause mapping in the Amazon. So we talk to those folks literally from the very beginning, before we write any code, to make sure that we understand what it is that we're trying to build and what success would look like from their perspective. Another big principle of AI2 and that underlies our work is openness. So we strive for open artificial intelligence research and development, and that means open code, open data, open training and evaluation. All of our libraries are open. The both pre and post training code are open. We open these libraries are on GitHub right now. You can look at all of this stuff if you want to. You can inspect exactly what we did. The models are of course available on Hugging Face, the weights I should say, and the training data that we use to build those models. So you can replicate exactly what we did, you can extend it, you can critique it, you can find flaws, and let us know, and we take that very seriously, and we care a lot about that. We also open source our production inference services, so a lot of the models I'm going to be talking to you about today, especially the applications, are literally they're running right now in production. The exact same code that we're running in production right now is available to you, you can look at it. And then the final big difference, I would say, is that rather than just a model, we really want to support the full ML lifecycle. And we see this as central to kind of putting the user at the center of development. So we are, in this case, I'll be talking to you about a platform that is the entire lifecycle of machine learning research and development, all the way from like raw data acquisition through training, or through annotation, training, and so on. So we really strive for end-to-end solutions, which we think are again, really critical for our users. And also these three principles really are self-reinforcing. Openness is really not a crutch, it's an advantage. And here are some examples of the applications that we've built on the AI for the Planet team. So some of these you may have heard of. This talk is going to be focused on the OlmoEarth, but I want to give you guys a little bit of a kind of motivation or like how we got to wanting to build this like big open platform. So these are a bunch of programs that have been around for, in some cases, many years, started at AI2. And Skylight, I want to talk a little bit about in detail because it offers some examples of kind of building these computer vision, these artificial intelligence models at global scale for real-time applications for a bunch of users. And it was kind of a key motivating factor behind the creation of OlmoEarth. So Paul Allen, and this is the AI for the Planet team, and I just wanted to recognize them. So this is a large team that's built all this technology, and I'm just one person. So Paul Allen, he envisioned a future where, so Skylight was started about 7, maybe 8 years ago, and Paul Allen thought that, eventually artificial intelligence would get to a point, and eventually there would be sufficient satellites in both frequency and revisit and everything that we would be able to basically constantly monitor the oceans, like remote, like high seas, basically, with computer vision. And this would enable maritime transparency, protection of marine protected areas, and basically have eyes on the water. And this transparency is, of course, critical to sustainability. So I'm going to talk a little bit about the models that we built that enable this. So one side of the models are satellite imagery-based detection. So this is like literally vessel detection on the high seas from a bunch of different satellites. Satellites are constantly orbiting the Earth, of course, and many of these sources are public data, so we can take them and do detection with them. And then the other side is GPS sequence modeling, which I'll briefly touch on. This is just a quick primer. A lot of people in this room are probably very familiar with how this generally works, but I just want to walk through very quickly. So we have activity in the remote areas, somewhere on the high seas. We get an image from an orbiting satellite that's downlinked to a ground station, eventually copied to our servers. We run a model against that, and then we serve this up via some API or GUI. In the case of Skylight, it's both, and this is serving currently a couple hundred or 300 or so organizations across like 60 countries. And this whole process occurs in like a matter of hours in the case of a satellite that I'm about to show in just 90 minutes. So we need to make these models extremely accurate, extremely reliable, because people depend on them, and people are literally making decisions with very limited resources on the basis of this information. So if you have a $50,000 fuel budget and we're saying we see some activity out here and in this marine protected area, for example, we better be right, and we care a lot about being right, and false negatives and false positives both cause big problems. So here's one example, just in more concrete terms, like what exactly we built and why. So you probably know different satellites have different strengths and weaknesses. VIIRS is a satellite that can see at night, so it's sensitive to light. It's actually exquisitely sensitive to light. You can pick out literally street lights on highways across the whole world. And if you have Earth at night on your phone or on iPhone or whatever, this is the data that's coming from. So the pretty pictures, it's called Black Marble, comes from this data. And there's several satellites now that are publicly available and support this particular sensor. So a couple great things about this satellite. We're getting real-time coverage, or near real-time coverage, I should say. It's about 90 minutes from everywhere on Earth, and that's really quite good, especially for satellites. It's global, it's providing global coverage, so that's excellent, literally everywhere, high seas, land, everything. There's roughly a 3 times a day revisit rate, which is really good, so you can see kind of successive pictures of the same vessel, but the spatial resolution is quite poor, relatively speaking. So especially if you're doing something like object detection or vessel detection, 750 meters is really not good. But you can see lights, and if you're doing bad things, you can probably turn off your GPS transponder, for example, but you can't turn off your lights, or it's much more difficult to do so. So we leveraged this satellite for detection, but it wasn't built for detection. It was built for clouds and for detecting clouds, for basically for atmospheric modeling, for atmospheric purposes, definitely not for vessel detection the way we've repurposed it here. So we've had to do some things to make it work, and this is roughly what that model looks like. So we have vessel detection, which in this case, this is a super simple model. It's literally a 2D CNN, like very fast, very efficient kernel with a bunch of other detectors for various sources of false positive that occur when you actually try to operationalize this kind of model. When we first got this model, so our initial version of this was literally just vessel detection, and we shipped that, put it into the service, looked at the outputs, and it was terrible. It was absolutely unusable, and we realized that we were detecting all these other things, which are sources of false positives, and so we decided we needed to build detectors for all of those. So over the course of building this model, we built detectors for gas flares, like oil platforms, lightning. Actually, this model is really good at detecting lightning if you need that. Aurora. Aurora is a huge source of false positives, and the Aurora move, you may have seen them last week. They were really far south. So all of these are sources of false positives. So you have to control for all of those. We built a model. It's a 2D CNN with these channels: moonlight, land, sea, clouds, and the nanowatch, which is the signal itself. So this model is tiny. It's like 40,000 parameters. It can be run as part of CI/CD, and it's very effective. I want to just briefly comment on the fact that, in general, when we do offline training, we see extremely high quality data, and it's fairly easy to make a really good model. When we ship that model, when we actually get into a production, it typically doesn't work very well. And most models generally don't see production, and so users are not going to see practical benefit. And so we think about this a lot, and one of the ways to address this is to make it extremely easy to get feedback from users. So I'm showing here a Skylight platform that's on the bottom, and notice how simple this is. This is literally as simple as it gets, right? You do not need a sophisticated detector to detect that that this is a vessel here. It's not always that simple. I'm showing a very simple example. It gets a little bit harder than that, but in general, we just show users, hey, this is what the model saw, and this is what it sees in the case of veers, and then just tell us if it's right or wrong, right? Our experts are generally, they will know, and they will be able to tell us, oh, that looks like a cloud or false positive or something like that, or we know it's a gas flare there, oh, it's a new platform, oh, it's a new wind turbine, whatever. So we just make it super easy to get feedback. The model that we were, I'm not going to use the word competing, but another model in the space that people were asking us to compare ourselves to was basically, this is how they provided feedback. It's the upper row here, and it's very difficult to interpret this, even if you know about signal processing and know how this model was trained. It's pretty difficult to immediately interpolate, oh, okay, that model was right or wrong, right? It's much easier to just look at the output. And we do this via feedback, and it's very effective. So we've done this for a bunch of satellites now, and we have computer vision. This is all operating right now at global scale in real time, serving about 70 countries. And we're covering these satellites, veers, so that's the one I just showed you. And then Sentinel-1, which is radar, that's synthetic aperture radar. Sentinel-2, which is optical imagery, and Landsat 8 and 9, which is also optical imagery. So all of these satellites, again, they have different strengths and weaknesses. We use them all at the same time, and users rely on these signals for different. So synthetic aperture radar, you can see through clouds. Veers at night, as I said. Optical is, of course, very useful. And so these models generally kind of work in tandem with one another, and users rely on all of them. They're quite performant at this point. We've been iterating for a while. They're right around, say, like 90 F1. They're very reliable. They're literally always on, and a bunch of users depend on them. They run at reasonably low latency, so 90 minutes for veers. It's hours or so for the others. And these run on T4s. These are super light models, and T4 is like, basically the cheapest GPU. I don't know, Google's probably going to turn them off soon at this point because they're so uncommon, but we get great utility out of them, and they work for these models. So everything here has been open sourced, both the models and the APIs, as I mentioned, and we provide this for free. You can go to this link actually if you want to see this. This is a public version of this. We have a public version of these maps, or of the kind of the outputs. Dynamic, and you can look. And actually, I'm going to show a few examples because I just think it's cool. Computer vision is fun. So this is some kind of fishing vessel with maybe a purse seine or something like that. Here's a vessel that we discovered. This was underwater. So in this case, we found like this shipwreck, basically. Here I'm showing, this is just outside of Boston. I just came up. This is what I found last night on the plane over here. And here I'm just showing you that like synthetic aperture radar, this is actually like quite hard to do this really well at scale. The signal is fairly faint. but we've trained this model on something like 50,000 expertly labeled annotations. This took years, just to be clear. Like one of the reasons I'm showing you all this is that I think there's a ton of value here, but it's really hard to extract. So this is synthetic aperture radar, and here you're just, so this is not optical. This is not what a human eye sees. This is what radar sees. In this case, this was positive, a positive detection, and radar sees through clouds, so that's very useful. We've also done global real-time modeling for the same platform, for the Skylight platform, with GPS data. And I'm just showing you a quick example here of what that looks like. So GPS data, I think, is generally another pretty rich source of information that is comparatively undervalued. GPS is usually transponded by every vessel on the ocean, unless you're like really a bad actor, and then you're probably going to turn off your, you're probably not going to constantly broadcast your location. But it's generally used by most vessels. And we can model GPS data really similar to how we model language data. The difference here is, of course, we have kind of this geolocation, lat long, plus a SOCOG, but we can just transform this into tokens in a way that transformers understand, do the standard thing in language model training. Here's the custom model that we built on top, and then we can get really high precision, high accuracy classification of all these GPS sequences at every moment in time on the whole world, in real time. So we're processing right now as we speak in Skylight, about 5 billion GPS, it's called AIS, Automatic Identification System, GPS messages per day. This is all running again on T4s. These models are pretty small. This model, I think, is on the order of, I think it's about 1 million or so parameters. It's super, super efficient, fast to run. And here we're providing, basically we're just telling all of our users what the vessels are doing at any moment in time, so they can go and intercept as needed if a vessel's doing something nefarious, or just knowledge of exactly what's going on. So this is happening, or these models are running in real time everywhere, and they're producing literally instantaneous classifications of the entire planet. With these models. This is outside of Boston. This is showing you in the last, I think it's a couple weeks or so, maybe month, just literally every single GPS message that was broadcasted from all the vessels that were in and around the Boston sea area, and what they were doing. We can use these same models to forecast human-wildlife conflict. So we haven't produced this model yet, but we believe we can take Earth observation data for land cover mapping, combine that with GPS data, combine that again with weather data to get a sense of what animals are going to do, especially around national parks where there's concerns for human-wildlife conflict. Human-wildlife conflict for elephants, for example, is the leading cause of death now for elephants. And so we believe we can do something similar here, take the Atlas models and basically forecast where there's going to be a conflict. This is just a pretty picture that I wanted to show you. This is basically all GPS data in the world in the last, this was I think 2024. This is roughly 5 terabytes of data, and it was just to force me to pause and think carefully. But yeah, this is just a pretty picture. So the net for us was that Earth scale modeling is generally pretty hard. All these models took years to make and to build and to ship. Each one was very different. We had to kind of do slightly different things, build the machinery to both train and then also to productionize and deploy them. And it was just very hard each time. It was fairly resource intensive. And we got asked to make tons of models. It's very difficult to do this at scale or for many different tasks. So you need expert labelers, you need machine learning research teams. This really is not a solved problem. You generally can't take off-the-shelf models and just make them work for this kind of use case. You need training infrastructure, thousands or maybe millions of GPU hours to train the base foundation models that do all these things. You need dedicated inference systems. And of course, you need to maintain these things if they're going to be productionized. So basically, this is out of scope for many nonprofits and NGOs. And we said, well, what if we can do this, for the world and make this a public good and really just kind of build it once, foundational infrastructure one time, and then give it away and let people kind of leverage the same technology that we've been using to build our models. And that's what the OlmoEarth project is about. That's what we just launched, as Sherry mentioned. And so the idea here is we have massive global scale real-time data coming from all different kinds of sensors, not just the satellites, but also there's ground sensors, there's buoys, there's weather balloons, there's all kinds of different sensors. Let's take all of these data, let's train a large foundation model with all of these sources, then let's integrate it into a full platform that enables actually leveraging this technology. And I'll show you what that means in a second. So we can empower many different, many different organizations, many different NGOs, many different users who want this technology but don't have the resources to get it. And we really think that this is the right time to do so. We think that artificial intelligence is about where it needs to be. The data is where it needs to be. We get asked literally by hundreds of organizations to build various models, and we kept saying no, honestly, and it was a bit heartbreaking because these organizations have extremely important missions that we want to be able to help, and that really is kind of aligned with our mission about building, artificial intelligence for good and for these challenges. And we didn't want to keep saying no, and so we said, let's build this platform, and that's called OlmoEarth. So OlmoEarth is this new, very new platform that we just released a couple weeks ago, last week, and it's a set of models that we also built, new foundation models that are state-of-the-art, a platform that enables leveraging these models, and then fine-tuning them for various downstream applications like ecosystem extent, biodiversity, conservation and sustainability, deforestation in the Amazon, forest risk assessments, all kinds of different applications that our users have come to us and asked, hey, can you build this model for us? And we said, hey, just give us a little time and then we'll have a platform that hopefully will enable you to build whatever you want. And so that's what we did, and that's what we've been building for the last year or so. So the idea here is we'll have a model, a foundation model that I'll describe in a second, and it's a foundation model that can do many different tasks really, really well. Across classification, segmentation, change detection, time series, non-time series, that kind of thing. And then a platform that enables fine-tuning these models and deploying them. So the entire ML lifecycle here, all the way from, again, raw data, annotate that data, deploy API, now you have a serviceable endpoint, whatever it is that you want. Maybe you want to download the maps, maybe you want to email the maps to a colleague, maybe you're the UN and you just need this kind of more from a policy perspective. We want to do all those things simultaneously so that users can take action. So maybe it's a real-time use case where users just want to know exactly what's going on right here, right now, and we have some applications that I'll describe that do exactly that. So OlmoEarth, as I mentioned, this is a new foundation model that we built, so it's very multimodal, so it combines many different satellites, many different sensors, plus some derived maps. It's multitemporal because we need to model changes over time. The Earth is obviously extremely dynamic. It's flexible, so it can run on whatever you have, whatever users have. Users typically don't have every imaginable modality. They may have one or none or whatever, and so you just want to be flexible for them. It can run even when you have missing data, missing time steps, it's no problem. And that's actually common because in production settings, satellites go down all the time, right? They go dark, whatever. So we need to be able to, we need to account for that. We also importantly want this model to be extensible. So in general, this was like a first step. We're trying to build a foundation, one that can be extended to many different modalities, many different sensors, basically whatever users have. We want to be able to meet them where they are. We want the model to be fine-tunable for many different tasks. So fine-tunable for basically whatever the user needs. And of course, we need this model to be open. We want the data to be open. We want the model to be fully open. You can reproduce this model. You can extend it. You can do whatever you want with it. What does the data look like? So in general, the data is, we consider it quite multimodal. So you have visual, infrared, you have microwave, you have radar. You also have elevation data and land cover, and you have many derived maps produced by many different organizations, OpenStreetMap, European Space Agency World Cover, World Serial. The US has produced a bunch of cropland data masks, and we can put all these into the model. In general, it's variable spatial resolution. So This can vary quite dramatically, and we need to account for that. Our current data sets right now, the ones I'll share with you in a second, they're training on fairly modest data, about 10 terabytes across these sensors. We have maps for world cover, cropland data, world serial, OpenStreetMap, and several others that I'll show you in a second. So this is what the pre-training data set looks like. So we have a bunch of satellite observations. These are all geo-referenced, so lat, long, and timestamps. And then we have a bunch of high quality maps, and we're putting these into a model. This is just the pre-training data that we're going to feed into the model. And then we have this covering about 300,000 locations. So you can see here the sampling is not uniform. It's obviously biased, and it's biased towards area where you have more data. And we certainly want to strive for even more data, and especially in the areas that are underrepresented here. And that's a major future effort. Here's approximately what the training recipe looks like. So I'm not going to cover this in detail, but we've published the paper a couple weeks ago, and you can look at that for details. But in general, what we're doing is we're pre-training via latent masked image modeling. And then we're doing kind of a fast version of that for high quality for the map data. So we're kind of combining self-supervision and supervision in this setup, so that we can leverage the data from both. And that ends up being quite effective. So OlmoEarth, we've shown, is state-of-the-art for a huge variety of EO tasks. We evaluated OlmoEarth, this new foundation model, against industry standard benchmarks, of course, research benchmarks that people have been using for a while. We also evaluated this model against our partner data, real world tasks that organizations have given us, asked us to do for them, crop type mapping, for example, or deforestation cause mapping, or wildfire risk assessments. And we've tuned these models for, we've massively benefited from those collaborations, because it's enabled us to make sure that our models do really, really well, not just on the research benchmarks, which are of course quite important, but also against these kind of maybe a little bit messier real world tasks. And so we've been optimizing for both, and we now have a model that performs really well on both. So on the left, you're looking at this OlmoEarth is now Pareto front for computational efficiency and performance across. This is showing the average on 13 different tasks via KNN and linear probing. So here we're taking just the embeddings from the model, so no fine tuning, and we're just saying, how do we compare to other major models in the field? And we're doing not bad. We're also doing not bad even for really small models. So you'll notice here that the VIT Tiny and the VIT Nano are actually quite good, and they're better than some much larger models. And that's significant because if you have a small model, you can retrain it faster, you can iterate faster, you can, its inference is much cheaper, of course, et cetera, et cetera. On the right, you're seeing fine-tuning. So fine-tuning is a bit different, right? There's a lot of variations in fine-tuning, and here we're doing relatively full fine-tuning. And, excuse me one second. What you're seeing here is average model rank. So OlmoEarth is on top. And actually, the VIT Tiny is also quite good. It's second best on these. This is 18 tasks. So this is 18 fine-tuning tasks covering a whole bunch of different segmentation, change detection, classification, et cetera, et cetera. Okay, I'm not going to ask you to look at this really closely. This is just to emphasize that we evaluated this fairly extensively on dozens of tasks, and then we also evaluated every other major model against those same tasks. So this is in the paper. The point of this is not to have you stare at the numbers, so forgive me if that's what you're trying to do right now. It's rather just to show you we've really done quite thorough evaluation. Top is KNN, bottom is SFT. We evaluated this model extensively, and performance of these models, this family of models, so OlmoEarth Nano, Tiny, Base, Large, is very good. It's generally the best or near the best. And that's a good thing, because that means that our users can leverage this model for many different tasks. The source code is available on GitHub. The weights are on Hugging Face, as I mentioned. But you can also access this model within the OlmoEarth platform. I just put an asterisk here. We recommend using the base model. For most tasks, large is generally better, but consult this table if you're unsure and if you have the spare compute. This was just super brief and just a taste. The ablations and results are in the technical report, which I'll provide well, if you go to olmoearth.allenai.org, you can see it there. Apologies, you can't see the URL here. And then Hugging Face and GitHub, of course. And I just want to shout out our infra team, Beaker, which does all the experimental management at AI2. So this is fairly hard to run all these experiments, and they've been awesome. And the language modeling team, that's the open language modeling team, Olmo, we've basically based these libraries off their core training code, which sped us up by a huge amount. I'll briefly comment here on comparisons to AlphaEarth. So AlphaEarth Foundations, you might have heard about, generated huge buzz and is probably largely responsible for that massive uptick we saw in the beginning in Google Trends. So Google came out with this model earlier this year, I think in June, something like June or July, and it generated a ton of interest, and that's a really great thing. And I want to emphasize that, in general, we are thrilled that so many talented teams are contributing models to this space. It's a great thing for the world when people work on this kind of technology. We're thrilled to see Google work on this. There's been a lot of activity recently, and it's generally just a great thing. And we really don't see it as a competition at all. That's not how we look at the space. We see it more as like, what can we learn from this? This is a great contribution to the world. And AlphaEarth and our model, OlmoEarth, they're quite similar in some respects. So they draw on similar data sources. If you've read the AlphaEarth paper, quite similar data sources, and they support similar downstream tasks. The big difference is that Google released annualized embeddings, and I showed you that performance of KNN LP earlier, and I'll show you again sort of how we compare to Google in a second. But they released annualized embeddings rather than the model itself. AEF embeddings are free to an extent. There's also a request for paste bucket if you need better scale. We have not released embeddings yet. We're thinking about it, and we may, but we haven't yet done so. We've released a model and a platform that supports kind of more customization, greater customization of these models. Why did we not just release embeddings? We certainly could. We think our embeddings are generally pretty high quality, as you've seen from the KNN LP chart. Full fine-tuning, we've found that full fine-tuning can significantly outperform frozen embeddings. And in our case, that means our users are going to get just better performance from doing fine-tuning. Fine-tuning is, of course, not trivial. The reason folks are excited about embeddings in the first place is that it's kind of this cached artifact that is easily shareable. And I can just give you embeddings, and then you're off to the races. And fine-tuning is not exactly like that. It requires a little bit more in-depth work with the model. There's an argument that embeddings are a lot cheaper than fine-tuning, and in general, I think that can be true, but when you think about the cost of these kinds of projects, when you're building an application that's dependent on this kind of technology, you're generally making a pretty significant investment, and it can be in many cases like months to years of effort. And that's like of FTE time and significant resources well beyond just like the model. So I think that in general, from our perspective, the cost of embeddings and fine-tuning may be similar. Maybe embeddings are a little bit cheaper, maybe not. But both are somewhat insignificant when you compare to the cost of real-world application development. So fine-tuning, for example, for the models that I'm going to show you in a second with our applications are on the order of like 24 hours of H100 time. So not that expensive, and especially or I shouldn't say not that expensive, relatively inexpensive compared to the cost of full application development. And that really is what I think matters most, at least to our users, and that's why we've chosen this route. Here's some performance. This is a table from our paper just comparing AEF and Helios. This is Helios. This is an old name, but Helios directly. So AEF is AlphaEarth Foundations. KNN is K-nearest neighbors. So this is just embeddings, just vanilla embeddings, whatever you get out of the box. So you can download these right now from Google. They made them all free, covering the entire world. These 5 applications here are from our partners. This is data that they've given to us, and then we've evaluated our models against their data. We've trained and evaluated models against their data. So NANDI is a crop type mapping in Kenya. AWF is land use, land cover classification from the African Wildlife Foundation. This is also, we have ecosystem classification here, live fuel moisture content. This is a measurement of wildfire risk, and then solar farm detection. So a fairly wide spread of applications here, and covering kind of various things you would do with geospatial foundation models. And we've evaluated this in a few different ways. Here I'm showing KNN, a frozen decoder setup, and then full fine tuning. Obviously you can't do full fine tuning with AEF because we just have access to the embeddings. So we're only showing you those results for OlmoEarth. Just try to ignore Helios here and just think about OlmoEarth as an old name. What I want you to kind of take home or take away from this is that yes, embedding performance can be really good. If we look at AWF, for example, the performance, the accuracy is in the 80s, and that's great, and that's out-of-the-box performance with embeddings. But we see fairly significant improvement from full fine-tuning. And on the left here, I'll draw your attention to NANDI. So this is crop type classification again. So this is a fairly hard problem within EO tasks. Crop type classification is extremely important. It matters like what we're growing. We need to plan for the future. We need to figure out how climate change is going to affect growing and so on. And so we want to do this really, really well. We find that fine-tuning, which again, in this case, I think it was something like 12 hours of H100 time, can generate a pretty dramatic improvement in performance. And this could very well be the difference between shipping and not shipping this model. We also measured the environmental impact, which we think is important to contextualize here. So here I'm just showing you the numbers, how many H100 hours it took to train these models for both pre-training and then for fine-tuning. Fine-tuning was a mix of hardware, and so I'm not showing it was variants of H100 and A100. And so we're just showing you the GP hours here, the energy, the carbon, and the water. We have a cluster, or we do pre-training on our own cluster at AI2, which is fairly energy efficient, and it's also very water efficient. It's closed loop, and so it's fairly water efficient in that regard. But we're obviously using energy. And here, just to contextualize these numbers, this is about what it would cost across all of these models. The energy was what it would what it would take to power an average U.S. house for 5 months, or an economy ticket and the carbon emissions are equivalent to an economy ticket on a flight from Seattle to Portugal. So this is the OlmoEarth team. This is the incredible team that built these models, and I just want to shout out all these very special people that built this. Applications. So I want to talk a little bit about applications, but before I do, I just want to say that the reason we even have applications is that we have a ton of partners that we've been collaborating with from the beginning of this project, and these are some of them. So in wildfire, we collaborated with, and for forest management, we collaborated with ACA, the Amazon Conservation Association, and NASA JPL. We've also been collaborating with the International Food Policy Research Institute, as well as the CGIAR, and more recently, the United Nations Food and Agriculture Organization, and very recently with NASA Harvest. And these organizations, these collaborations were integral to the work that we did throughout this project. They literally are really centering and anchoring our work. So let me show you a few examples of wildfire and forest health. And I'm also going to ask Sherry how I'm doing on time. It's 4:50. I don't know when you want me to stop. 5 minutes? Yeah. Okay, I'll speed. I'm going to go faster. Just kidding. I'll just focus a few examples. So wildfire and forest health. So I'm going to skip this. So we can take these models, these base foundation models, we can fine-tune them on a bunch of ground truth reference data from DNR, forest DNR employees who go out into the forest and collect collect wood samples, take them back to the lab, dehydrate them, and then weigh them, and that's a measurement of moisture. You can imagine that that process that I just mentioned doesn't scale super well. We discovered that we can take these models that we built, fine-tune on those expert samples, and then produce wall-to-wall coverage, so entire Pacific Northwest or entire United States at like literally the cost of a few cents. It's just a little bit of H100 time. And so we've done this in a few areas before and after fires to see if they work. And the net here is that it's about 1 million times cheaper. You still need that reference data. You cannot do this without reference data. You need the experts going out into the field to collect this data, but enables you to scale in a way that is just otherwise impractical. We've also looked at deforestation in the Amazon. I mentioned this earlier. So on the right, you're seeing a map that we've produced of Amazon with Amazon Conservation Association. So we're producing deforestation maps, specifically what the cause of deforestation was. Was it farming? Was it a landslide? That kind of thing. So these are time series models, OlmoEarth trained, fine-tuned with expert data from the experts from Amazon Conservation Association. And we're yielding roughly a 3 order of magnitude over what the 10-kilometer norm was before. We've done work with the Global Mangrove Watch with these same models, and we've been partnering with the Global Mangrove Watch from the beginning, actually. In this case, they gave us, or we worked with them on training a new model, an OlmoEarth model, so base foundation model, again, fine-tuned on expert GMW data, and we can get about roughly similar performance that they were getting with their 5.8 million training points with like literally 10K samples. And that enables them to spend more time doing the important work that they're doing, less time, hopefully, on the things that, on, say, data annotation, so they can do their work. We can accelerate their work. Okay, one more example, Sherry, and then I'll wrap up. I want to highlight one more example, and this was with the International Food Policy Research Institute. So we need to map crops at scale. We need to do this really, really well for a whole bunch of reasons, for policy, for farmers, for planning, for climate change, for many different reasons. And currently, this is like an unsolved problem in the space. And we think you can do a pretty good job, and we're not the only group to do this, just to be clear. In fact, Sherry is one of the labs that has done this really well, but we are generally trying to do this well at scale with very few samples. It's a really hard problem. So we were approached by the International Food Policy Research Institute. They say, hey, we have all this data. Can you train your model on our data and see if you can get good results? And we got pretty good results. So on the left table here, you're seeing a random forest. This is from IFPRI. On the right, you're seeing literally first pass from OlmoEarth, and the results were quite good. And now I'm going to go lightning speed, Sherry. So OlmoEarth is designed to close this gap from foundation models to our users, and we've built a whole platform that enables everything that I just said to give people access to this technology. So all the foundation models, applications for, we built all of this, and we've made it available all the way from data acquisition through annotation, labeling, deployment, serving, and we have a web app, and this is now available, so we're making this all free. We think this should be a public good, as I mentioned, and we think we'll do better by working together. So this is approximately what it looks like, and I'm gonna skip now to the last slide. Like I even said, otherwise skip, time permitting. There's a lot of interesting stuff in there that will be for another time. So this is kind of what I wanna end or leave you with, is that I think this was a step in a step towards open, accessible, and more holistic modeling of the Earth. I think we have quite a long ways to go, clearly, and I think our approach here is to build open artificial intelligence, really in close collaboration with partners. We of course welcome new partnerships across research, engineering, obviously fieldwork, policy. And in general, I would just end with the idea that we have a responsibility to steer artificial intelligence for the benefit of all humanity. So thank you so much for your time.